Hey guys, IBM is here with part 5 of solved past paper questions for magnetic fields and electromagnetic induction. This is Physics 9702 past paper questions up to 2025. And if you want the solution document to these past paper questions, you can inbox me, you can write to me. However, the typed solutions are not really free. So in part 4, I think we stopped on question 9. I want us to go straight to question 10. So electrons are moving in a vacuum with a speed 1.7 times 10 to the power of 7 meters per second. The electrons enter a uniform magnetic field of flux density 4.8 milliteslas. The figure shows the path of the electrons. So we see the path of the electrons. Okay. Then the path of the electrons remains in the plane of the page. State the direction of the magnetic field. Of course, we use Fleming's left-hand rule to tell the direction of the magnetic field. So using Fleming's left-hand rule, because the electrons are negatively charged, we reverse the second finger to point in the opposite direction to that of the electron, because the second finger of Fleming's left-hand rule is supposed to point in the direction of the current. And we know that electrons move in the opposite direction to current. So if electrons are entering the field from the left-hand side, then the second finger must point towards the right, because the electrons are entering towards the right-hand side. So the second finger must point towards the left. So at this point here, putting the second finger towards the left, as shown in the diagram here, and we know that the force, because this is an arc, it means the magnetic field is causing the magnetic force is causing centripetal force. So the force is acting towards the center. The center of the arc is in this direction here. So in other words, it means the thumb is going to point downwards. The second finger is pointing towards the left. And by Fleming's left-hand rule, notice that the first finger points into the page, into the plane of the page, as demonstrated by this finger here. Therefore, it means the magnetic field is into the plane of the page. So this is into the plane, into the plane of the page, into the plane of the page, or simply into the page. You could also get the same result if you use Fleming's right-hand rule. For the right-hand rule, you don't reverse the second finger. You just maintain the second finger in the direction of the electrons. So if the electrons are moving towards the right, and using the right-hand rule, the force is downwards towards the center of the circular path, so the force is downwards. Still, you notice that the first finger points on into the plane of the page. So in all cases, the field is into the plane of the page. Show that the magnitude of the force exerted on each electron by the magnetic field is given by 1.4 times 10 to the power of minus 14 newtons. So we know that force on a charged particle is given by BQV in the magnetic field. And B is 4.8 milliteslas. V is 1.7 times 10 to the power of 7 meters per second. And then EQ is 1.6 times 10 to the power of minus 19. So this is going to be 4.8 milliteslas. That's times 10 to the power of minus 3. Then Q is 1.6 times 10 to the power of minus 19. Then V was 1.7 times 10 to the power of 7 meters per second. So this is 4.8 exponent minus 3 times 1.6 exponent minus 19, then times 1.7 exponent 7. So that is 1.306 times 10 to the power of 1.306 times 10 to the power of minus 14. which is approximately 1.3 times 10 to the power of minus 14 newtons. Like I always emphasize, the examiner wants to see the answer which rounds off to what is given unless it is exact. On the figure 6.1, draw an arrow to indicate the direction of the centripetal acceleration of the electron where it enters the magnetic field at point X. So of course, the direction of the centripetal acceleration is the same as the direction of the centripetal force. The centripetal force and the centripetal acceleration always act towards the center of the circular path. So at X, the arrow must point down towards the center, and I had already drawn that to show the direction of the force. So this is the arrow. That means I'm going to wrap this other arrow here so that I only remain with that one. So to answer that question, the arrow must point towards the center of the circular path. Okay. Then next, use the information in B Roman 2 to calculate the distance d between the path of the electrons entering the magnetic field and the path of the electrons leaving it. We want the distance d between the path of the electrons entering the magnetic field and the path of the electron leaving it. In other words, we want the diameter of that circular path. We can first find the radius. We have said that the magnetic force provides centripetal force. So in other words, the force due to the magnetic field is going to be equal to the centripetal force. And the centripetal force is equal to mv squared over r, but the magnetic force is equal to bqv, which is equal to 1.3 times 10 to the power of minus 14. So I'll say 1.3 times 10 to the power of minus 14 is equal to mv squared over r. So the radius is going to be equal to the mass of the electron, which is 9.11 times 10 to the power of minus 31. The speed was 1.7 times 10 to the power of 7. This is squared. Divide by, I'm making r the subject, so I will divide by 1.3 times 10 to the power of minus 14. So from my calculator, 9.11 exponent minus 31, then times 1.7 exponent 7 squared, divide by 1.3 exponent minus 14. So that is 0.0202, which is 0.02. So this is approximate 0.020 meters to two significant figures. So the diameter is twice r, which is going to be 2 times 0.020. So the answer here is going to be 0.040 meters. The electrons in B are replaced with positrons that are moving with a speed of 3.4 times 10 to the power of 7 meters per second along the same initial path as the electrons. The positrons enter the magnetic field at point X. Now positrons, these ones are positively charged. That means they are going to be deflected in the opposite direction to that of the electrons. So if the electrons are deflected downwards, the positrons are going to be deflected upwards. Also look at the speed. The speed of the positrons is twice the speed of the electrons. And since we know that the centripetal force equals mv squared over r, it means that the radius is directly proportional to the speed squared. So since the speed is now greater, it means the radius is going to be greater. So v is doubled. Since v is doubled, v has been doubled, then it means the radius is going to be 4 times. So the new radius, new r, is going to be 4 times the original radius. The new radius is going to be 4 times the original radius because r is directly proportional to v squared. Now that v is doubled, so twice v squared is going to be the same as 4v squared. So it means the new radius is going to be equal to 4 times the old radius. Remember, the radius is equal to the diameter is equal to twice the radius. So the new diameter the new radius is going to be 4 times the new radius is 4 times the original radius. And remember, diameter is equal to twice r. And since the new radius is 4r, it means the new diameter is going to be twice the old diameter. Because in 4r, we have two diameters. In 4 radius, we have two diameters. So the new diameter is going to be twice the first diameter. So you may not actually measure, but if you want to be very accurate, you can try to measure. So I'll try to measure here, even though this is not to scale. So this is approximately 2.5 diameter, 2.4. So the other one is the new diameter is going to be 4.8. 4.8, because this is a positron, it is going to be deflected upwards. So the new diameter is going to be about 4.8. So it will be around here. So I'll draw, because it's a bigger diameter, so it means the curve is going to be bigger. You try to make this bigger. Let me try to make it bigger and more beautiful. The entry point is the same. So this is going to be then it is going to emerge from this point. So use a ruler to draw that path. So the deflection is going to be different. So I'm saying this diameter here is approximately twice this one here. So this is twice d. So it is a positron, so it deflected in the opposite direction to the electron. That means the force acts in the opposite direction to that of the electron when they enter a magnetic field, because the positron has an opposite charge. Number 2, the speed was twice. Therefore, the radius is 4 times. The diameter is going to be twice the original diameter. Okay. Then a heavy aluminium disc has a radius of 0.36 meters. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field of flux density 0.17 teslas is switched on. The magnetic field is perpendicular to the plane of rotation of the disc, as shown. Define magnetic flux. Of course, we know the magnetic flux is B times A, where B is perpendicular to the where A is perpendicular to the magnetic field. So this one is the product of the magnetic flux density, that is B, and the area, normal to the magnetic field, or normal to the direction of the magnetic field, or perpendicular to the direction of the magnetic field. That is, flux equals to B times A. Alternatively, I said you can write flux phi equals to B A sine of theta, where theta is the angle between the direction of flux, B, and the area A. Calculate the magnetic flux through the disk. Give a unit with your answer. So we want to find magnetic flux. So flux equals to B times A. And of course, we know that the area is, because this is circular, so it is pi r squared. So this is going to be, B is given as 0.17 teslas, and the radius is given as 0.36. So this is going to be 0.17 times pi times 0.36, and this is squared. So pressing my calculator, so this is 0.17 times pi times 0.36 squared. So that is 0.069. Of course, the units of magnetic flux is the Weber. So the answer here is going to be 0.069 Weber. The disk is rotating at a rate of 25 revolutions per second. So that means time for 1 second, time for 1 revolution, or period, which is time for 1 revolution, is going to be 1 over 25, because there are 25 revolutions in 1 second. So period is 1 over, so this is like the frequency. So frequency is equal to 25 hertz. So the period time for 1 revolution is 1 over 25. Then calculate the magnitude of the e.m.f induced between the axle and the rim of the disk. So in the time is going to be 1 period. And we know that induced e.m.f equals to the rate of cutting of flux, or rate of change of flux linkage. Rate of cutting of flux, or the rate of change of flux linkage, which is going to be change in flux divided by time. And this is going to be, the change in flux is going to be 0.069. Then the time in 1 complete period, that is 1 divided by 25. That is in 1 cycle. Because in 1 cycle, the flux changes between 0 to 0.069. So that is 0.069 times 25, which is 1.7725 volts. So this is going to be 1.7 volts. The axle and the rim are connected into an external circuit that enables the energy of the rotation of the disk to be stored for future use. The direction of rotation is shown in figure 6.1. Use Lenz's law of electromagnetic induction to determine whether the current in the disk is from the rim to the axle or from the axle to the rim. Explain your reasoning. Okay. So when you look at the diagram here, I want you to notice that if the rim is rotating in the direction which has been shown by the arrow, the disk is rotating in the direction which has been shown by the arrow. We know that Lenz's law demands that the force must act so as to oppose the rotation. So if I consider a situation where, let me just consider this point here. Okay, let me consider this point here. If the rotation is, let's say, clockwise, the force must act anti-clockwise according to Lenz's law, or it must act counterclockwise. So it means when employing Fleming's left-hand rule, the force must be acting counterclockwise at any point. So if this was acting clockwise, the force must act counterclockwise, which I represent by this thumb here. And the magnetic field is towards the right, so the first finger must point towards the right. And if you try to make the thumb to be in the counterclockwise direction of the rim, of the rotation of the rim, you notice that by Fleming's left-hand rule, the second finger points towards the center. So if I consider this point of the rim, the second finger is pointing towards the center. If I consider this point of the rim, remember the rim is rotating clockwise, so it means the thumb must be pointing counterclockwise, which is into the page as shown here. The first finger must continue pointing the same direction. And you notice if the thumb is into the page, with the first finger into this direction, the second finger is pointing towards the center. So it means by all means, at all positions of the rim as it rotates, by Lenz's law, the force must act so as to oppose the rotation. And if the force acts so as to oppose the rotation, then the direction of the induced current is going to be pointing towards the center of the rim, which is actually towards the axle. So using these hands which I've added here, you can predict that the second finger, which shows the current, is always going to be pointing towards the center of the rim, which is towards the axle, at any point where you apply them. When you apply it at the top, since this is clockwise rotation, the thumb must be in the opposite direction, which is this one here. With the first finger pointing to the right, the second finger points towards the center. That's towards the axle. If you use it at this point here, remember rotation is in that direction, so the thumb must be counterclockwise. And if we do that, the first finger in this direction, the second finger is again going to point towards the center, that is towards the axle. So the second finger is always pointing towards the axle, which indicates that the current is going to be flowing towards the axle. Okay, so I'll just put this in writing and say that the induced current in the disk is perpendicular to the magnetic field. Induced current in the disk is perpendicular to the magnetic field. And so if the induced current is perpendicular to the magnetic field, it means that the current causes a force to act on the disk. And so the current causes a force to act on the disk. So the current is going to cause a force to act on the disk, because if the current is perpendicular to the magnetic field, Fleming's left-hand rule can apply. So the three fingers must be at 90 degrees. According to Lenz's law, the force opposes the rotation of the disk. According to Lenz's law, the force opposes the rotation of the disk, and by Fleming's left-hand rule, by Fleming's left-hand rule, the current is from the rim from the rim to the axle. I think that was easier to visualize. The current is from the rim to the axle by Fleming's left-hand rule. So I want to explain this again for easy understanding. So if the rim is rotating clockwise, as shown by this arrow here, the force according to Lenz's law must act counterclockwise. And remember, by Fleming's left-hand rule, the thumb points in the direction of the force and the first finger points in the direction of the magnetic field. With the first finger pointing to the right, the thumb pointing counterclockwise of the rotation of the rim, the first finger points downwards. You can try that with your left hand and see. So that means if the second finger is always pointing downwards, that is, it is pointing towards the center of the rim. That is, if you used it at the top here. If you use Fleming's left hand rule at the bottom, remember the rim is moving clockwise, so it is going like this. So the force must be counterclockwise, which is actually into the page. Then if the thumb points into the page, with the first finger pointing to the right, the second finger points towards the center, which means the current is from the rim towards the center where we have the axle, so it is from the rim to the axle in all cases. That is in accordance to Fleming's rule. Okay, so that is, I think that is the question, and I want part 5 to stop on this question. See you in part 6. Do not forget to subscribe. Do not forget to download. You can leave a comment. You can write to me if you have any question, if you have any concern. I'm always willing to solve most of your concerns. If you find any errors in this, you can always just leave a comment. I don't mind. I don't mind to rectify. Until next time, it's IBM. Bye bye.